Hey there, folks. Calc folks, to be specific. We're back here looking at some more Mathematica. Looking at using Mathematica here in our calc class. Looking at it. So far, we've looked at some fundamental arithmetic and some of the basics of algebra that we're sometimes asked to do, right? Things like expanding, factoring, simplifying, solving, right? Those are all skills of algebra, right? And we're going to add to those skills with this lecture or this demo, whatever you want to call it. And we're going to look at, we're going to look at user-defined functions, defining functions. We're going to look at making tables, right? And plotting, graphing. Right? Mathematica calls it plotting, right? Those are our topics for today. If we flip over here to Mathematica, I've already set up that title. We're going to look at some user-defined functions, tables, and plots. All right? To begin with, not only does Mathematica have its own functions built in, for instance, it has the sine function built in, or the cosine function built in, right? Or the exponential function built in, right? It also has the ability for a user to define a function. For example, I could define function f of x, right? Now, we might define f of x to simply be x squared, right? Maybe that's what I'm looking to define f of x as. And the way that I define f of x as a function in Mathematica is as we see here. You can see how this formed, right? Our function, right, might be named f, and it is going to be a function of variable x, where in Mathematica, to help Mathematica recognize in the language here that we are defining a new way of we are defining the dependent values for this function named f, and helping Mathematica recognize x as the independent variable, right? What we follow that independent variable x with inside the name of the function here is the independent variable with a little underscore, right? And you can see when I go over to the right-hand side now and I say, well, this is going to be set equal to something, you can see how that notation behaves. Here you can see that x has kind of become italicized and turned green, and said, okay, there's going to be some sort of input here that follows with respect to x. And that is going to be maybe x squared, right? And if I hit that as an input, then I have defined the square function, right? Or maybe I define the function g of x equals the line 2 minus 1/3 x, right? Yeah, there's 2 minus x divided by 3, right? That is our function g of x. I can, with this notation now, go about calling f at x, right? Or I can call up f of x at any point in time, right, and get back x squared. And I can call up f of x at other input values, right? F at x plus h is h plus x quantity squared, right? I can take two functions and add them together this way. I can take f of x and add it to g of x and build a respective function, right? The sum of those two functions. Or I could take f of x and multiply it by g of x, and maybe multiply that all by, what did I do here? Let's leave it alone there, and find that product. I can call up values of f. I can say, well, what's f at 4? We should note that that's 16. Right? Or I could call up what is f at negative 3. We should know that is 9. Or maybe I make h of x right, equal to f at x times g at x, right? Define that function and call up h at -5 in value. Oh, oh, you can see what I made my error there, right? I did not declare that properly as a function. I just can't call it h of x. I have to call it h of x underscore, right? Highlighting we are declaring that as our function. And now when I come down here and I declare h of -5, I get a respective result. All right. You know, that's just working with that function notation there, folks. All right. You're going to work with that function notation quite a bit in calculus, right? In this work, with working with Mathematica and working with calculus in general. Most of our formulas and theorems and definitions are all based upon functional behavior, right? And incorporate functions into their calculations. All right. What else can we do with a function? Well, we can make a table with this function. Let's look at making some tables. This would be the table command. We can make a table of f of x values, right? And the way we would declare that table is we would say, well, table, wrap our function f of x with a table command, and then we inside the command have a comma, parentheses, where inside the parentheses we're going to say what values of x we want to table over. Let's start at 0 and go up through 10. Now if I hit enter, you can see I do make a table of values that starts at x equal to 0 and goes up through 10, where it squares f of x each time, because remember that was how we define f of x. Is up above we defined f of x as x squared. Right? So it's going through from 0 to 10, plugging it into the function and telling us what the output is. It's making a table of those values. Right? It is incrementing by 1 each case in the table. You could have it increment by a half if you were to follow the 10 with the change in values there. And certainly, right, adding this then tells it what to increment by. We could do it by halves. We could do it by tenths. Right? If we input fractions, you will notice that Mathematica will say, all right, you want to work in fractions? I can work in fractions. Or if you want to work in decimals, you can put in decimals, and Mathematica is perfectly all right with working within decimals. Right? If we want to divide this up over some interval of x, maybe we want to take from 0 to 10 and divide this into 3 subintervals. Maybe we subdivide it into 10/3. Right? And now we've divided from 0 to 10 into 3 equal subintervals. From 0 to 100/9, from 100/9 to 400/9, and from 400/9 to 100. Right? The values of f of x have been divided up equally. Right? Those would be the corresponding outputs. If we wanted the corresponding inputs, we could make a table of tabled values. Right? Because notice what the output of a table is. The output of a table is itself just a set of values. Right? So we can input a set of values into a table and make a table for a set of values. And here's the table for the corresponding coordinates, right, for this subinterval, or subdividing f of x into 3 equal portions. Right? Let's go back and look at just from 0 to 10. Mm-hmm. We may be interested in, this is a horizontal arrangement, and that works nice when working with the screen visually here. But maybe we want to look at things as a column. And you could wrap that table command with the column command, and you get more of a tabled appearance to this. There is also some grid commands out there, and you can make some grids with tables, tabled values, and you can certainly explore all that in the help menu. But here, we're just looking at some of the basics. Right. So that is working with tables, folks. Right. And that is the column command. You can just wrap the table command with the column command and end up with that table of values. All right. Now, what if we wanted to look at the plots seen here, right, actually laid out in a graph? To lay out actual points in a graph, that is the list plot function, right? And we're going to list plot our, well, what we're going to list plot here are going to be our tabled values. What I'm going to do is I'm going to go up here in this table, and I'm going to call this table 1. T1 is equal to this table 1. And actually, let me bring this command up here and follow T1 and put it all into the same cell here, you can see. I haven't inputted anything yet, and in fact, let's go up here and delete all my output so I kind of, freshen things up. This is all the output I've run through so far. We still can see f of x is up here, and maybe before we go any further down here, let's redefine f of x in this stage. All right, let's say f of x again is equal to x squared. We have a table being made in this cell. Delete that. Right. Here we have a table of f of x is also happening in this cell. If I scroll up, you can see that there. Where we're also going to want to make a list plot of, now, we can call out individual coordinates inside list plots, but we do have to wrap them. The entire input into a list plot itself needs to be wrapped inside a set of braces. It needs to be presented as a set of items itself, right? So we could make a list plot of these elements and table up what we have there. And you can see I get that plot. I get 0, 1. I get the plot 1, 3. Right? But I could also inside there, instead of 0, 1, and 1, 3, I could plot the tabled elements from T1. Now, T1, you can notice, already wraps those values representing those coordinates in themselves a grander set of parentheses. So I don't need the outermost parentheses here on this when I input this table into Mathematica. Right? And you can see there is that tabled plot. Right? The plot of the tabled values seen above there. Right? There are some different plot options when you're making plots. You can, first of all, label the axes. So we might put in here a label axes. And notice here I am just axis label is the plot option. And notice inside plots, once you define what it is you're plotting, you can put in a comma and then follow it with a list of plot options. One of those plot options is labeling the axis, and that would be axis label. And notice I am doing a minus following that, followed by a greater than sign. And it's going to make this arrow shape, where now I'm going to label my axes in parentheses, and I'm going to use I'm going to label my axes inside braces using parentheses around my x value and parentheses around my y value in the order x comma y, right? To define the coordinates as the x and the y coordinates in this table values. And I do use parentheses because then it approaches x as a text bit of information. I put these in parentheses so that it's reading it as text and not as an input variable. If I was to make it an input variable like f of x, right, it would actually spit out x squared when it labels that axis. See? If I scroll up, you'll be able to see there it labeled that axis with an x squared, because for that horizontal axis, I put in there f of x, and I didn't put it in. And let's change this around. Let's make this x. And if I put over here f of x, it's certainly going to say this is x squared. If I don't want it to say x squared and I just want it to say f of x, I'd wrap that in some parentheses, and it'll read it as text information now. And then furthermore, I could even say something like it's y equals f of x, right? And it reads that all as text, and it labels that vertical axis as y equals f of x. All right. Other plot options you can set is if you don't like the aspect ratio, you can always change the aspect ratio. I find automatic sometimes works nicely. Right. What automatic does, well, automatic, let me say, works nicely if you're trying to get things into proper scale. If you want your x-axis to scale with your y-axis, you would set it to automatic. Right? If you were to, what are our options here? Aspect ratio. Full is another option. Right? And it does try to, I don't know what it does specifically for full here, but it does capture a nice visualization of that shape. You can also set it, for instance, you could set it to a 1-to-1 ratio, right? Which I think full might be doing. Maybe we set it to a 10-to-1 ratio, which would kind of morph it one way, make it into scale one way, or maybe we set it into a 1-to-10 ratio. All right. You could look at setting different ratios of scale here. Right. Here's a 1-to-2 ratio in scale. Right. That's setting aspect ratio. I'll put that on full. What's another plot option we can have? Ticks. Right. You can do automatic on ticks. You can set how often you make ticks. You'd have to look into that. What I often do is if I'm removing ticks, I'll use the option of none. Right? You can actually remove ticks from your graph. All right? I think if we're looking for grid lines, if you're looking for more grid lines, you could set some grid lines to be automatic. Or you can look into some of the other possible options for setting up grid lines. Right? If you're looking at changing color or look to your plot, that would like to what your actual dots look like in your plot. That would be plot style. Right? Our plot style here, we could change them to red in color, and they will become red. If you want to have more than one plot style, you have to wrap those styles in the directive operation here, or command. So maybe I want to make their point size. This is how to make bigger points a little bigger. We maybe go 0.03. And you can see we can get some bigger points in our graph, folks. All right? Just playing around with some plot styles there. There's a lot of options you can have in a list plot, and you can see them all if you went underneath your help menu and you went into the documentation, right? And you looked up list plot. Right? There are several different ways that list plot is inputted, right? Right now we are looking at making list plot in really the second way here, as a list of points, and we're putting them in as tabled values. Right? Down here in details, you see a lot of the different plot commands you can have. Right inside there. And then here are all the Down below here, list plot, these are all your graphical options. All right. Plot labels, plot legend, plot style. All right. If we wanted to look at plot style elements, you could click on plot style and come over and see you can dashing, you can change the colors, point size, thickness. If you're talking lines, you can make them actually kind of give a glowing essence to them. There's a lot of edge form if you're making bounded regions and whatnot here. There's all sorts of different plot styles here, folks. You can read into those, folks, but that's all underneath the help menu. Again, clicking on the little, if you're on the cloud, it would be the little magnifying glass up in your upper right hand corner up over here. Right now, that is the first of the plots that are kind of fall into our fundamental scenario. The second is the case for making just a regular old plot. We could also just plot f of x and consider plotting f of x over values of x from 0 to 10. And we could get a respective graph seen here. All right. And if we wanted to, we could come along with some more plot options inside this plot. We could say here, let's make it, let's label our axes, and actually copy paste works nice for that. Maybe we go full, well, let's just copy paste that, just to save us the time. Let's not turn on grid lines here, but let's do plot style. And let's certainly make the line maybe, let's add some directive. Let's make it black. Let's make it dashed. And then let's change the thickness. Now, you can set the thickness by value. Right? Or you can actually just call it out as particular thicknesses. Right? There's thick. I think I could get away with thin. Right? There's a lot of different ways to declare those values, right, in your plot style. Right, we could go, there's a lot of different colors like magenta, right? Magenta is that a nice pink, or you could go green. Green works, right? Or you could do light colors. Maybe you like light blue, or even I think you could get into some of the RGB colors and options. All right. Those are all just setting different directives. Instead of dash, maybe you want dotted. You can do dotted. Or just remove it altogether. Excuse me. Notice here, it does give us a little bit of output for this input of 115 here. It does tell us x squared. It does give us the function y equals f of x in its graph, right? Its plot form. It does give us the tabled values, and then it does give us the plots. What might be nice is to get rid of some of this output, right? This is a lot of output coming. How you can turn off output is you can follow a line of code in Mathematica with a semicolon. That's first of all one way to turn off output. For instance, we could turn off, right, our functional declaration and our tabled values, right, that we use in the list plot, right? And we could see there that that added information does disappear, and you could also follow your plots with semicolons and have them disappear respectively, right? However, it's saying, do you really want that to go away? Right? So another idea that we can also do here is, certainly those are two separate plots, What might be nice is to combine them into one, and that is where the show command comes in, folks. I could show these two plots at once. What I will have to do, though, is go up and call them, like I did the table, of a particular name. So maybe I'll call this plot 1, and I'm going to refer to this as plot 2. And I'm going to consider showing plot 1 with plot 2 as a command. Don't know. Did that not show up? Oh, yeah, it did, right? Down here is plot 1 and plot 2 combined together. Again, if I don't want these now, I could follow those with a semicolon, and Mathematica says, yeah, I got no problem with that because you have called them out, right? Don't lose track of them there, but then it just gives the one value, right? The one graph in the picture here. You will notice that it did adopt plot 1's descriptions, right? Plot descriptions, right? The axis label is plot 1. The plot style in terms of certainly is not really something that it grabbed, but then it didn't really give us the aspect ratio of full here. It went with the default ratio here that plot gave. One thing you'll notice is that is all based upon the order in which we put these in the show command. If I was to switch the order and put in plot 2 first, followed by plot 1, it's going to default to plot 2's plot options. And you can see that is the case now. Now it labeled the axes different. It included the grid lines. It made its aspect ratio different. All of that, folks. And then on top of that, you can at times even mix in commands here. For instance, a good command is image size. Right? Certainly, if you get too big of an image, you can certainly shrink down that image size. Right? Make a smaller graph. You can call it out by physical size, or you can call them out by, I think is it pixel distance? Right? Pixel size. Respectively. Right? So there are different ways to manipulate the size that way. Another plot option that sometimes comes in handy is plot range. I don't know if that works down here. You can actually call out different range values, automatic, full, all, or you can actually plot out a specific range of value. So it does work down here, and that works also up in your plot options. I'm trying to think, is there other things here? You can call out specific values. Right? For instance, in this plot, I might be interested in calling out f of x. Let's call out f of x. What do I mean by that? Let's point to it in the graph. And say, hey, there's f of x. Did it show up here? It did not show up here. Now, one of those reasons maybe because of these plot options. Let's watch the order here. That has no effect. Let's get rid of this image sizing and plot range, because everything was really nice to begin with. And I don't like that at all either. Man, we've really gotten this buggered up now. When things do go awry on you, you can always go up to cell and delete all output, and under evaluation you may find delete all output. But under evaluation you also find quit kernel, and you can quit the kernel. And then every once in a while that will fix any bugginess you might be encountering here. So all of a sudden things have gotten really out of control, bugginess. Let's turn all these back on. It's making my table, but it's not plotting it now. Oh, you know why? Again, this is a common mistake. When I declared my function f of x, I didn't really truly declare it. It was still going with the one above. Now it should work a little nicer. Ah, that's a common issue, folks, you're going to run into. So let's close that off. Let's not spit out that output or this output or that output and just grab the end game. Right, just this issue here. Right, just that image there. Right. Then so you can see here what it is doing. It is calling out y equals f of x. All right. You can also position that a couple of different ways. You could say, well, let's position it above. Right, and it pops it up above. You could go below. Right there, it's gone down here and positioned it left. Right. So it's down over here, hidden along the x-axis. So you can see not all positions are optimal, or you can even call out a position, like maybe we want to put it at 8, 8,80 in the graph. And really what that 8,80 aligns, it kind of aligns the little hook in the point. All right, folks, when pointing over at the graph. So we can call out it that way. If it's too small to visualize, you can wrap your text in the style command. And what the style command does is allows you to give it certain color, I believe, and size. You have to call them out in a certain order. Let's see here. No. All right, I don't think so. But we called it out red, and we made it 30 in size. Now, I think that is a percentage of the overall, maybe x-axis, right? So maybe we want to scale that down. Certainly 15, maybe. All right. So those are, and notice all I did was wrap my text in the call out command with a little style options there. I was able to get a different style or look to that. All right. Folks, we're at about 30 minutes, a little over 30 minutes here on this demo. Again, what I wanted to show you here was a little bit of work with user-defined functions, folks. You can define user-defined functions. That common mistake, I was making that common mistake up here, folks, where, what is it? You do have to, when declaring your functions, make sure that you follow your independent variable in the declaration with an underscore. All right. I did have that mistake down here in my, what might be my little program that I've written here to make this graph and table and all that. And then we looked at how to make some tables, how to make some plots, right? Some common plotting, like just the plot command or the list plot command, the table command, and how, what are some different plot options, some useful plot options that might go into all that. I'm trying to think what else is there, folks. Set declare, that's the other thing, is I have set these equal to things. You can also do what's called set declare, where you do a colon equals. And what set declare does is it, certainly as the code reads, it says, oh, hey, P1's right here. When P1 gets called up again, I'm going to come back to P1. Oh, here's T1. When T1 gets called again, I'm going to come back to T1. Oh, here's P2. When P2 gets called up again, I'm going to come back to P2. And what you don't need are the semicolons at the end, right? The function f of x lies undeclared until the plot calls for it in P1. And P1 lays undeclared until the show command calls for it in the very end of the process. All right? The T1 command lays undeclared until the list plot calls for it. The f of x, right? And I should say f of x lays undeclared again until the T1 function calls upon it. And that's called the set declaring. So you'll notice when I input this, it gives me the same output, but it doesn't give me any of the other inputs, right? It doesn't declare f of x as it would if I would leave that as just an equal to, all right? What this is doing is it's declaring f of x to begin with. Hey, everybody, f of x is x squared. So use f of x squared, or use x squared every time you see f of x. So right away, this is, when P1 is being read, it's putting x squared there. And when T1 is being read, it's putting x squared there. And when, those would be the two locations where f of x would be being used. I will tell you the set declared, folks, is sometimes beneficial to use, and sometimes it's better to use a declared value. Sometimes we just use set declared to be quick and avoid having to use the semicolons at the end, whereas sometimes it's better to issue a declared value. So we're going to see that and encounter that in the work. You'll see me at times just set declare because I'm in that mood, and sometimes just use a semicolon because I'm in that mood. But sometimes I'm going to have to use them specifically. So I will make sure that I point that out in any future demos. And we might encounter some instances where it's important to use one versus the other. Be able to point out, those issues. But again, 35 minutes in here, I need to stop this video at this moment. So I'm going to stop there. We're going to come back and look at... Are we at the point of calculus? I think so. Well, let me come back and show you some limits. How to do limits on Mathematica, how to do derivatives on Mathematica, and how to do integrals on Mathematica. Right? Let me show you some of those advanced operations on Mathematica. I think that'll be our next video. And either in that video, depending on length, or the next one, maybe we'll look at writing our first program. Look at doing some programming in Mathematica. Just to get us in the, looking at what we are possible to do. We actually see a bit of programming here when we're looking at this here. This cell represents a program, and if you actually hit Alt-8, right, you can actually highlight that entire cell. Right? I don't know if this shows up on the video. This often doesn't show up on my videos, but what it'll do is it'll highlight, if you just click inside there and hit Alt-8 on your keyboard, it'll highlight that cell using a coding format, and it'll highlight that that's all one code waiting there to be run. And what does that code do is it makes this graph down here with these points on it for our function. Could I give a different function? Yeah, you could give a different function. Maybe you're interested in negative x minus 4 quantity squared plus 6. What does that graph look like? Ooh, I got some issues there. I don't know what we're encountering with this. I may have regretted doing that. I don't see what the issue is with just changing that over. But certainly there might be something buggy in the code. You can always go into evaluation, and there might be a board evaluation. Let's delete all output. Let's quit kernel. And just see if that doesn't fix our problem. And if not, I may need to look at what is the problem here. It might ask you to initialize all cells in the notebook. I often click just no. And here we're still issuing some problems. But let me, I'll have to figure this out in a future video. But let me end here because we are at time, folks. So, I'll be back with more. See you soon.